Okay, so now that we've seen the gravitational potential as well as the field strength intensity, let's do a couple examples to see how we actually calculate this thing. So the first one we're going to look at is something that we looked at back when we originally looked at the gravitational field, which is we're going to consider a spherical shell of mass m of constant radius of capital R. And we want to know what then is the potential at some point P, which is some distance R away from the central point. So to do this, we're going to do exactly like what we did back then, which is we're going to cut this thing into a whole bunch of rings, where each one of these rings is going to have some differential mass dm. So again, if I look at this from, in this case, this is the side view. But again, if I look at it from a top view, this is my top view. Again, I'm chopping this thing up into a ring, where this ring then has a differential mass of dm. So if I look from here, then the S is going to be from the top of this ring to that point of P. R then is from the 0 to that point of P. And then I'm going to define the angle of theta, which is then from the origin here up to R, and of course I'm going to take my mass here at the origin itself. Now, since this is a continuous charge distribution, what that means then is we're going to say that the gravitational potential, which again is equal to the sum over all of these alphas. The alpha, we're going to let then that m alpha goes to 0, so we're going to take the limit of the sum, which simply means that we're going to do an integral. So we're going to integrate this guy then as g times dm all divided by s. Okay? Where again, dm is then differential mass at which I'm then integrating. So I'm chopping this thing up into a whole bunch of small pieces, calculating the potential from each one of these different rings in this case, summing all those together, which means I'm simply doing an integral. Now, good. G, of course, is just simply equal to a constant. dm, as we've done before, we're going to write that in terms of a geometry type integral. So in this case, since I'm chopping it into a ring, so in this case, we're going to write then that what? So dm is going to be equal to what? The mass density of this guy, so let's call that rho, times then the differential area of the ring. So rho then is simply going to be equal to a constant since this thing has constant density to it, and then dA is simply going to be equal to what? The circumference of the ring times then the thickness of the ring, which in this case is going to be equal to d theta in this case. Right? So basically my thickness of my ring is going to be here, so this is my thickness, which is going to be dl, but then using arc length, I can rewrite dl as simply r times d theta. So we insert an r here as well. So the circumference of this ring basically is only going to depend on this radius r here, so that is what? This radius across here of r. So from here I can see that r then is equal to r sine of theta, where the circumference is the same thing as 2 pi r. So it's going to be the same thing as rho times r times the circumference, which is then 2 pi times r times d theta, which is the same thing then as rho times r times 2 pi r sine of theta, d theta, which is then going to be what? 2 pi rho r squared sine theta d theta. So putting this in here, then what we can say then is our gravitational potential is going to be equal to 2 pi times rho times r squared times g times then the integral of sine theta d theta all divided by s. So basically from here what we want to do then is what? Rewrite either s in terms of theta or theta in terms of s, because what? If I choose different locations, right, the different distances of s are going to change as theta changes, which means theta is a function of s or s is a function of theta. So the way we're going to do that is to use the law of cosines. So from here, let's write the law of cosines. So the law of cosines, remember it says that what? this side squared is equal to this side squared plus this side squared minus twice of this times cosine of the angle between the two, which is r theta in this case. So we can then say s squared then is equal to capital R squared plus little r squared minus 2 times r times then cosine of theta. So now from here, these two things are simply constants. So if I take a derivative of both sides, what I get then is that 2s ds is then equal to minus 2 times r times the derivative of cosine of theta. But the derivative of cosine of theta is equal to negative sine of theta d theta. So this is going to be 2 times r times sine of theta d theta. So the 2's are going to cancel. So ultimately what this says then is I can rewrite then sine of theta d theta in terms of SDS. So good. So let's plug that in here. So what this says then is that sine of theta d theta is then equal to what? S divided by r times ds. So let's plug that in here. So this is going to become equal to 2 pi rho r squared g divided by r, because those two things are constants, integral of then s ds divided by s. And in this case, I'm going to integrate from the shortest distance s can be, which is going to be the same thing as r minus capital R, to the greatest distance it can be, which is then r plus capital. So I'm going to introduce r minus capital R to r plus capital R. Now in this case, these two r's are the same, these two s's are the same, so we're simply going to cancel those out. This r is going to cancel with one of those, so this is going to become 2 pi rho times r g divided by r times the integral of ds, which is simply s. I'll evaluate from the bound, so I get r plus r minus and r minus r. So basically the little r's are going to cancel. The two r's are going to give me a 2 capital R. So this is going to become 4 times pi times rho times r squared times g divided by r. And I just realized I forgot my negative sign out front. So there should be a negative here. Negative, 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 negative. Sorry about that. Good. Now, rho, we know is the mass density. So rho is going to be equal to what? The total mass divided by the total area. Well, in this case, since it's a spherical shell, what I care about then is the surface area. And the surface area is the same thing as what? 4 pi times the radius of this guy squared. So here, the 4 pi's are going to cancel. The radius squared is going to cancel. So at the end of the day, this becomes minus g times m divided by r, which basically says then that what? The potential on the outside is exactly that of a point mass whose mass is concentrated directly at the center at the origin of this coordinate system. Now, as we talked about when we originally talked about gravitational force, this is not unexpected because, again, Newton's universal law of gravity tells us that for an extended object, all of the mass acts as if it's at a particular point, where with a regular shaped object such as a sphere, it acts at its geometric center, which in this case would be at the origin. So this is not unexpected. This is something we've already seen. So we're not going to be surprised by this. Good. So the next example we're going to look at is we want to know what is the gravitational potential in the plane of a ring of charge whose mass is m and has a constant radius of r. So what is that? So it means here is my ring has a constant radius of r and a mass m. And I want to know in the plane, meaning anywhere within here, what then is the potential at any given point. Now, ultimately what that means is we're going to have to look at two different points. So basically for part A, we're going to have to look at some point out here. So this is going to be my point P, where then this is going to be my distance of r. And then for part B, we have to choose some point on the interior. So let's choose this as my point P, where this is now going to be my distance of R. So basically just meaning that for part A, we're going to look at when R is greater than capital R, so meaning we're on the exterior. And then for B, we're going to look at when R is less than capital R, so we're on the interior. So, now here, I'm going to look at some small mass here. So let's call this my dm. So that this distance, again, from here to here is going to be my s. Again, I'm going to define this angle of theta. Again, that's my r and my capital R. So good. So again, we're going to simply say that the potential, gravitational potential for part A, is then going to be equal to, again, minus g times the integral of dm divided by s. So again, we're just going to simply say we're chopping this thing up into a whole bunch of differential masses, figure out the potential at point P from every single one of those differential masses, sum them all together. So again, we're just going to do an integral. Now in our case, dm though is going to be equal to lambda, where lambda is then the mass density, or the linear mass density, so that's the mass per unit length, times then the differential length. Now again, if we think about the differential length, I'm going to chop this thing up this way. So even though this has a differential length dl in this direction, that's the same thing as the theta here. So again, I'm going to use arc length. I'm going to rewrite this as lambda r times d theta. So in this case, we're going to integrate over theta. Now in this case, I'm going to integrate from this position over to this position. So we're going to integrate this from 0 to pi. I'm going to rewrite this as minus g times lambda times r, because r is a constant, integral from 0 to pi, then d theta divided by s. Now to find s again is not independent of theta, as we saw from the last problem. So using exactly what we did in the last problem, s then is going to be the same thing as r squared plus capital R squared minus twice of r little r times then cosine of theta. Now in this region, we know the fact that what? R is greater than capital R, which means we're going to pull out an R from here. So I'm going to rewrite this then as R times the square root of 1 plus R divided by R, quantity squared, minus 2 times R divided by R times cosine of theta. And let's define then that x is equal to capital R divided by little r. So I'm going to rewrite this then finally as r times the square root of 1 plus x squared minus 2x cosine of theta. So let's plug that in here. So this becomes equal to minus g lambda r over r, because that r is a fixed constant, integral from 0 to pi, then d theta, then the square root of 1 plus x squared minus 2x cosine of theta. To do this integral, it turns out you can actually do this integral one of two ways if you want to do it exactly. The first way is you can actually use what are known as elliptical integrals. So it turns out you can find an exact solution using elliptical integrals, even though an elliptical integral, it's defined in terms of an elliptical integral, which is something you usually have to do numerically. Or you can use Legendre polynomials to rewrite this in terms of the generating function in terms of Legendre polynomials, and then do the integral that way. Again, if you're comfortable with Legendre polynomials and kind of have a good understanding of what those are, you can use that. If not, another way we can do this is we can look in what's known as the far field limit. So let's do that one. So let's look at the far field limit, which means we're not only going to have r greater than r, but we're going to have much, much greater than r, which basically means we're going to force this point to go very far away. Now, what that's going to allow us to do is that, in this case, what that means then is x, which is defined as r divided by little r, And the far field limit then means that this is going to be much, much less than 1, which is going to allow us then to Taylor series expand this denominator. So if we Taylor series expand that denominator, that'll then allow us to kind of have a better approximation of what this thing actually is. And again, r divided by r here is actually the same thing as x. So here, if we Taylor series expand, this is going to become approximately equal to minus, we pick up a factor of 2 from this Taylor series expansion. So it becomes minus 2x lambda g, integral from 0 to pi g theta. And I'm going to skip a step here, but I'm going to collect all the appropriate terms together, and I'm going to write this only to order of x squared, which means I'm going to write this as 1 minus x squared divided by 2, plus x cosine of theta, plus 3 halves x squared. See, I'm running out of room here, so let me make this a little bit smaller. Move it over just a little bit. So this is going to become g is approximately equal to minus 2x lambda g integral 0 to pi d theta 1 plus x squared over 2 plus x cosine of theta plus 3 halves x squared cosine squared of theta plus terms which go as order x cubed and greater. Now, so here, note to do this integral, I can do this as a whole bunch of different integrals. So first off, if I do the integral from 0 to pi of just d theta, that's simply going to be pi. This one is the same thing, so x is independent of theta, so this is also just going to give me a pi. This one, so note that if I integrate 0 to pi of cosine theta d theta, that's the same thing as the integral from pi to 0 of d sine of theta. But if I integrate d sine of theta, that's the same thing as sine of theta, evaluated at 0, which is 0, minus evaluated at pi, which is also 0, so this thing is simply equal to 0. And if I integrate 0 to pi of cosine squared of theta d theta, then this is going to be equal to pi divided by 2. So basically what that means then is when I integrate this term is going to go to 0. This term here is simply going to give me a pi over 2. This term is going to give me a pi, and this term is also going to give me a pi. And then again, higher order terms, we're not going to worry about those for now. So this is then going to be equal to my gravitational potential minus 2x lambda g times, well, every term has a pi in it, so let's go ahead and factor out the pi. And then I'm left with a 1 plus, now I have two terms which depend on x squared. Oh, sorry, I should have been a negative, not positive. Sorry about that. So then I get an x squared times, so from here I get a 3/4 minus a 1/2 from here. And again, plus order x cubed terms. So from here I get a 3/4 minus a 1/2, but a 3/4 minus a 1/2 is the same thing as 1/4. So it's going to become minus 2x lambda g pi times 1 plus x squared divided by 4. Now in this case, let's write out lambda. So we know lambda, again, is the mass per unit length. So lambda is going to be the same thing as the mass divided by the length of this. But the length of this is simply the circumference, which is then 2 pi r. So here, what's going to happen is the 2 pi's are going to cancel. I'm going to have left a mass here, and then, so I'm going to have the 2 pi's canceled, so I'm going to have m times g divided by capital R, but then from here, I get an r divided by little r, so the capital R cancels, so this is going to be gm over r. So putting everything in, let me erase some stuff here. So I finally get that the potential is equal to minus gm over little r times then 1 plus capital R squared over 4 times little r squared. Plus higher order terms. So terms that go as r over r quantity. let's look at the field strength intensity. So let's look at G. So we know that G then is going to be equal to minus the gradient with respect of the potential. Now in this case, since only dependent on R, nothing here actually depends on theta, so this is going to be equivalent then to minus the partial derivative with respect to R of that potential in the R hat direction. So if I plug that in, so this first term then, so if I look at only the first term, so that minus is going to kill off that minus, but then I have a 1 over R, derivative of that is a negative 1 over R squared, so it's going to give me a negative GM over R squared. This term then is going to give me a negative from here, but again, the negative here cancels that out, so that becomes a positive. So I'm going to get an R squared over 4. And then when I take the derivative of that, that's going to give me a negative 3 over R to the 4th, plus then terms, which are going to go as the derivative of this guy. Let's just write it then as R over R cubed again for now, with a GM. So I also need my GM here. So we can factor out then that negative. So negative GM over R squared. And then I get a 1 plus 3/4 R squared over R squared plus higher order terms. So basically what this says then is what? Kind of in an intermediate region, this thing doesn't go as 1 over R squared. It actually goes as 1 over R squared plus 1 over R to the 4th plus 1 over R to the 6th, and etc. But as I get further and further and further away, this thing acts like 1 over R squared, so this thing becomes simply the same thing as a point mass at the center. Which again, we should expect, because if I get far enough away from anything, it should look like a point mass. So good. So that's on the exterior. So now what we want to do is do this again for the interior. So get rid of all this. So basically, everything we just had stays the same, except when looking at S, instead of factoring out a little r squared, I'm going to factor out a big R squared. So remember, S was equal to the square root of little r squared plus big R squared minus 2 little r big R cosine of the angle. So in this case, I'm going to factor out a big R squared. So I'm going to get a big R square root of 1 plus little r over big R quantity squared minus 2 little r over big R cosine of theta. In this case, I'm going to define a new variable y, which is going to be equal to little r over big R. I'm going to write this in as r square root 1 plus y squared minus 2y cosine of theta. Now again, to simplify the problem, we're going to take, in this case, not only is r less than capital R, but it's going to be much, much less than capital R. So I'm going to take r is much, much less than capital R. So again, I can do a Taylor series expansion. So my phi of g then is going to be again minus, where were we? So minus g times lambda times r. Steal my paper. Integral from 0 to pi of then 1 plus y squared minus 2y cosine of theta, square rooted d theta. Again, let's do our Taylor series expansion and then collect, again, only up to y squared terms. So it's going to be a minus 2g lambda r, integral from 0 to pi, d theta of then 1 minus y squared over 2 plus y cosine of theta plus 3 halves y squared cosine squared of theta. Same thing as before, when I do the integral over theta, this term is going to become pi. This term, I'm going to pick up a pi. This term is going to go to 0. This term is going to become a pi over 2. So this is going to be then equal to minus 2g lambda pi r times, and again, the pi comes from the fact that I'm factoring out the pi. So again, I get a 1 plus y squared over 4. Same thing as before. Here, I get a 3/4 minus a 1/2. So that becomes the same. The only difference is now I have a difference in what y is. So plug everything in, what again in this case is this becomes minus gm divided by r times then 1 plus r squared divided by 4r squared. So from here, my field strength intensity, again, is going to be equal to minus the partial derivative with respect to r of this gravitational potential in the r hat direction. Again, doing all the derivatives, so basically this term here has nothing to do with r, so this first term is going to go away. This one is going to get down a factor of 2. The negative here will be canceled with the negative, which actually means it's going to become positive. So I get a gm over 2r cubed r in the r hat direction. So the interesting thing here is actually notice that the acceleration due to gravity, or the field strength intensity here, is actually positive and not negative. So basically what this means then is if I have my particle, say something around here, what's actually going to happen is it's going to feel a repulsive force in this case, causing it to move outward away from the origin, as opposed to when it was out here, my field strength intensity was negative, which means it was actually going to feel an acceleration towards the center. So here my acceleration is actually away from the center, where here my acceleration is actually towards the center. So it's actually interesting here that this actually becomes repulsive due to that plus sign, as opposed to an attractive, which it was on the exterior. So these are a couple examples of how to actually calculate the potential as well as the field strength intensity for the gravitational potential.